In the last part, I'm just going to show you the concept of linear transformation of random variables and how the expected value and the variance of random variables are affected by the linear transformation. Now, the name linear transformation may seem to be something very complicated. However, it is not. What is linear transformation? It's a linear function of real numbers. Okay, so let's just say a and b are arbitrary real numbers, and ax plus b is called a linear transformation of variable x, or a linear function of variable x. So this is linear transformation, ax plus b, with any arbitrary real numbers of a and b is called a linear transformation of x, ax plus b. Now, why do we define such a thing? Why do we call this a linear transformation? Because linear transformation is going to be a very useful tool for us, and we are going to use it very frequently. And at this point, we should put a name on it, and we should call it a linear transformation. Now, here's a linear transformation. You know, if you measure the temperature with a Celsius degree, you can also convert it to a Fahrenheit degree. How? By multiplying the Celsius degree with 1.8 and adding it 32. So what you are doing is actually you are scaling the Celsius degree with 1.8 and shifting it further with 32. Another linear transformation example is this. We can define a random variable x, and if we multiply that random variable with an arbitrary real number, it can either be positive or negative, or it can even be 0. In this example, a is equal to -2 and b is equal to -5. It is also negative. So we are not supposed to give positive real numbers. In linear transformation, I can use any real number, and -2x minus 5 is also a linear transformation of random variable x to random variable y. So we can apply linear transformations over random variables as well. Now, why am I teaching this? Because this is going to be very helpful for us in the future. So at this point, let's see how the expected value of a linear transformation is calculated. So my friends, let's just say a and b are any real numbers. They can be 0, negative, or positive. And we are interested in calculating the expected value of a linear transformation of random variable x. And according to this proposition, the expected value of ax plus b is equal to a times the expected value of x plus b. So this means if the interior of the expected value is a linear function, you can simply take this multiplier and the increment term, or in other words, the slope and the intercept outside the expected value, and you can calculate the linear function of the expectation. So in other words, the expected value of a linear function is equal to the linear function of the expectation. So obviously, when I say this to you, you will definitely believe that. However, I want to show you the proof of that. So how this is true, how this can be correct. And let's calculate the expected value of ax plus b for a continuous random variable x. Let's make the proof of this for the continuous case. However, you can also do the proof of discrete random variables. It is going to be very similar, but I'm not going to do that. So expected value of ax plus b is what? You know, when we are calculating expected value of x, you were multiplying x with fx. When you are calculating the expected value of x squared, you were multiplying x squared with fx. And when you are calculating the expected value of ax plus b, obviously you are going to multiply ax plus b with fx and integrate it from -infinity to +infinity. And you know, because fx is a common multiplier here, you can distribute it over this summation operation, and you can write ax times fx plus bfx. And the integral of the summations can be re-expressed as the summation of separate integrals. So instead of integrating the summation, I can first calculate the first integral in the summation operation and then the second integral. Or in other words, I can distribute the integral operation over the added terms here. And you know, a here is a multiplier. It's a constant value which can get out of the integration. And if it gets out of the integration, in the integral, there only remains x times fx. And you know, this integral is equal to the expected value of x. So the first component is a times the expected value of x. And let's check the second component. In the second component, we have b as a constant multiplier, again, which can get out of the integral. And in the integral, the integrand, the function that we integrate, is fx simply. And if you integrate a probability density function from minus infinity to infinity, what you are going to get is the total area under the PDF. And I have told you earlier that the total area under the PDF is always 1. So here is 1, and the result here is a times expected value of x plus b. So you see the proof is very simple. For the continuous case, for the discrete case, you are only going to replace these integrals with the summation and fx with the px, the probability mass function. And the result is still going to be the same. So this proof shows us the expected value of a linear function of a random variable can be obtained by the linear function of the expectation. And now we are going to see how we can calculate the variance of a linear function of a random variable. Again, we assume that a and b are two arbitrary real numbers, and we are interested in calculating the variance of ax plus b. And how do we compute it? According to this equation, according to this proposition, the variance of the linear transformation is not equal to the linear transformation of the variance. So in the expectation, you can easily take the multiplier and the increment out of the expectation. However, in the variance, it doesn't work like that. You cannot take the b outside. B does not change the variance. B does not change the variance because what? I have told you that the variance is a measure of spread over the real line. So how the potential values that this random variable can take over the real line are spread. It is measuring this. Now, for example, we know the variance of the output of a die was 35 over 12. Now I am telling you this. If I, instead of writing integers from 1 to 6, if I write integers from 101 to 106, which means I am adding up 100 to each value on each face, then the variance wouldn't be affected because still the distribution is going to be over 6 consecutive integers. The spread of the potential values over the real line is going to be the same. However, if you multiply the values, for example, if I multiply every face of a die with 2, then the outputs are going to be 2, 4, 6, 8, 10, and 12. You see the spread of the potential values that it can take is increasing. So there is a wider area of the potential values that it can take over the real line. Therefore, we say that if you multiply a random variable with a, then this multiplier can get out of the variance by squaring it. So variance of ax is equal to a square variance of x. So the constant multiplier gets out of the variance by squaring it. However, b does not get out of the variance. So let's prove that statement as well. We are going to calculate the variance of ax plus b. And this time, in order to give a simple proof, I am going to use the classical definition of the variance. Remember, what was the classical definition of variance? We calculate the expected value of the square of the deviation from the mean. So if we are interested in calculating the variance of ax plus b, we need to first find expected value of ax plus b and subtract it from ax plus b, and the difference is going to be squared, and in the end we are going to calculate this expected value of the squared deviation of ax plus b from its expectation. Now this is the classical definition of the variance of ax plus b. Now let's do this. Let's start with expected value of ax plus b. So remember from the previous proposition, in an expectation of a linear transformation, the multiplier and the increment can get out of the expectation. So here becomes minus a times expected value of x minus b. And automatically you will see that b's will cancel out. Okay, so b is gone. There is no addition of b anymore. So this is simple as it gets. B is not effective in changing the variance. However, we have AX minus A expectation of X. A is a common multiplier here when B is cancelled out, and we can take this A out of the parentheses. However, remember, there's a square term here. Therefore, A can get out of the parentheses as a common multiplier, and we need to square it as A squared. And because A squared is a constant, again, it can get out of the expectation without changing it, just like here, as A goes outside the expectation without a change, A squared gets out of the expectation without any change. And we have A squared times expectation of the squared deviation of X from its expectation, which is defining the variance of X. So this is a very, very simpler proof compared to the previous one. As you can see, the variance of a linear transformation is simply equal to the A squared times variance of X. So only the multiplier gets out of the variance as squared. If the multiplier is negative, then when you square it, it is going to become positive. So you need to be careful about this. Why? Because the variance of a random variable can never be negative. So when you take a negative multiplier outside, you need to square it. And when you square it, it should be a positive value. So we have only 2 more questions to solve. Suppose we modify a die. So there is a die, which is a fair die, let's just say. And we modify this die by multiplying the numbers on each face with 2, and then we subtract 5. So what happens to this new die? This is a modified die. We multiply every face with 2 and subtract 5. So this die is going to have outputs as -3, -1, 1, 3, 5, and 7, right? So let's just say y is a random variable which denotes the outcome of this modified die. So it says calculate the expected value of the output of this modified die and calculate the variance of it. Let's just use the linear transformation idea. So we define random variable x as the outcome of a regular die, which is not modified yet. So from question 9 and question 14, you can see that expected value of a regular die is calculated as 7/2, which is 3.5, and the variance was 35/12. This was the expected value and the variance of a regular die. Now, how do we modify the die? By multiplying each face with 2 and subtracting 5 from each face after multiplying it with 2. So the output of the modified die is going to be 2 times the output of the original die minus 5. So the random variable y is defined as 2x minus 5, which is a linear transformation, right? So the question is asking me, what is the expected value of this modified die? And expected value of y is equal to expected value of 2x minus 5. And we know from the previous propositions, in a linear transformation, both the multiplier and the increment can get out of the expectation without any change. Expected value of 2x minus 5 is equal to 2 times expected value of x minus 5. And since the expected value of x is 3.5, we multiply 2 with 7/2 and subtract 5. This new modified die's expected value is 2. Finally, the variance of y is what? The variance of y is equal to the variance of 2x minus 5. And again, from the previous propositions, we say that this minus 5 will not affect the variance. So it is not going to change anything. We are just going to remove it. And 2 here is going to get out of the variance as squared. And this is going to be equal to 4 times the variance of x. And we have already calculated the variance of x as 35/12 in question 14. So the variance of this modified die is going to be 4 times larger than the variance of the original die, because we are simply multiplying the values with 2. So that's actually a simple explanation of the linear transformation and how the expected value and the variance can be calculated through linear transformation for some random variables. And we are just going to do the same for this random variable here. it says we have random variable x, which is a continuous random variable with the following PDF. So if you remember this PDF from the earlier questions, I guess question 22 and 25, we have already calculated the expected value and the variance of x in these questions, in question 22 and 25, I guess. And the probability density function is 2x. However, the question is asking us to calculate the expected value of 3 minus x over 4 and the variance of 3 minus x over 4. My friends, maybe it is going to seem a little weird at the moment, but these functions are linear functions as well. So 3 minus x over 4 is basically minus 1 over 4 x plus 3 over 4, right? So the multiplier term in front of the random variable is minus 1 over 4, and the increment term or the intercept of this linear function is 3 over 4. So this is also a linear transformation. So if the question asks us the expected value of 3 minus x over 4, we can rewrite this linear function in this form, and the multiplier and increment can get out of the expectation. And from question 22, we have already computed that the expected value of this random variable is 2 over 3. And by plugging it here, we can calculate the expected value of 3 minus x over 4 as 7 over 12. And just like that, we can also compute the variance. Again, 3 minus x over 4 can be rewritten as minus 1 over 4 x plus 3 over 4. 3 over 4 is not effective in changing the variance. However, minus 1 over 4 is effective, and it should get out of the variance as squared. And the square of minus 1 over 4 is 1 over 16. And the variance of x were 1 over 18, as we have solved it in question 25. And the variance of this linear transformation will be 1 over 288.